A warm greetings to everyone. Today I am going to present a video under my project topic titled Application of Dynamic Programming Technique to Reliability Model in Space Mission. Now we are going to see introduction, definitions, dynamic programming formulation to a reliability model, and then conclusion. Introduction. A mathematical framework for analysis and forecasting the performance of intricate space systems is offered by reliability modeling. Systems are frequently shown as series parallel or series parallel configuration in traditional dependability models and use component reliabilities to calculate overall system reliability. The project titled Application of Dynamic Programming Technique to Reliability Model in Space Mission presents an analytical study on the use of dynamic programming techniques to evaluate and improve reliability in space mission systems. The project is well organized into 4 chapters, each dealing with different aspects of the topic and providing a systematic understanding of the problem. In Chapter 1, the project introduced the fundamental concepts of reliability and the dynamic programming. This chapter provides the background needed to understand how reliability plays an important role in complex engineering systems, especially in space missions where failure of a component may lead to the serious consequences. The chapter also explains the basic idea of dynamic programming as an optimization technique used to solve multi-stage problem efficiently. This mission can be broken into discrete phases including launch, orbit intersection, operation and termination for the purpose of space mission reliability modeling. But too much redundancy makes the system heavier and expense. Two important limitations in space mission by striking a balance between resource constraints and reliability enhancement. Dynamic programming aids in establishing the ideal redundancy levels. Applications in space missions are redundancy management, autonomous fault handling, maintenance scheduling, spare allocation planning, degraded mode control, long duration mission planning. That in chapter 2 focuses on the basic definition and the formulation of the dynamic programming problem applied to a reliability model. Important terms and concepts related to reliability analysis are clearly defined. The chapter also explains how dynamic programming can be used to model reliability problems by breaking them into smaller subproblems and solving them step by step. The formulation is presented in this chapter forms the theoretical foundation for the analysis carried out later in the project. Reliability. For practicing engineers and manufacturers, sales managers and consumers, economists and government officials, it has become a major worry. More productive use of resources is made possible by a well thought out and efficiently run reliability program, which also reduces waste of funds, materials and labor. Series configuration. A series combination is the most basic arrangement of units that make up a system. Additionally, this is one of the most widely utilized structures. Let x1, x2 up to xn stand for the successful functioning of these separate units and p of x1, p of x2 up to p of xn for their corresponding probabilities. Every one of the n units must operate efficiently for the system to be successful. Therefore, probability of x1, x2 up to xn is the probability that all the units will operate successfully and simultaneously. Parallel configuration. There are numerous systems whose effective operation is depend upon each of their n subsystems or components operating satisfactorily. Additionally, we can have a system where the same operation is carried out by many signal routes and the system will function well if any one of these parts operates satisfactorily. Assume that units 1, 2 up to n respectively are successfully operated by x1, x2 up to xn. Likewise, Let x1 bar, x2 bar up to xn bar respectively stand for their failed operation. Series parallel configuration. There are several redundant elements in each stage. Stage I is made up of ni superfluous elements connected in parallel. Stage 1, stage 2 up to stage k are all connected in series to the form of the system. The system's dependability is given by Ri is equal to 1 minus product over j is equal to 1 to ni into 1 minus p of xij. The system reliability is given by the equation R of s is equal to R1, R2 up to Rk, that is product over I equal to 1 to k, product over j is equal to 1 to ni into 1 minus p of xij. Redundancy. We could improve system reliability by employing the redundancy establishment technique. This requires the deliberate creation of new parallel paths for the system. Assuming the elements are independent, their product is always less than P of A or P of B because both P of A and P of B are less than 1 on their own. Therefore, all P of A or B is all P of A or B is greater than or equal greater than P of A or P of B. The notations used in dynamic programming are Ci, M, 1 plus Xj, Pj of Xj, Xi, where Xi varies from 0 to Mj. In chapter 3, the project provides us numerical examples to demonstrate the application of the dynamic programming technique in calculating reliability. These examples help in understanding the practical implementation of the mathematical model. By solving these examples step by step, the chapter illustrates how reliability values can be computed and how optimal decisions can be made in reliability planning for space mission. Let us consider an example. Space missions. As a spacecraft has 3 critical subsystems. Redundant components can be added, each with weight and cost implications. Objective: maximize mission success probability while respecting total weight or cost limits. Objective: maximize z is equal to p1 of x1 into p2 of x2 into p3 of x3. Constraints: c1x1 plus c2x2 plus c3x3 less than or equal to 1,30,000. We know that the system reliability is R of s is equal to product over I equal to n to k into 1 minus product over j equal to 1 to ni into 1 minus p of xij. For maximum reliability, we have the formula given in equation 2. The optimization value in the n stage is given by the recursive relation in equation 3. Here we substitute n equal to 3 in equation 2. We get psi3, the value of psi3 is equal to 7. We substitute k equal to 3 in equation number 3. We get psi2 is equal to 7 minus 3x3. If we substitute k equal to 2 in equation 3, we get psi1 equal to psi2 minus x2. The table represents the admissible values for psi2 and psi1. We get these values by substituting the values for x1, x2 and x3 in the equations of psi1 and psi2. We know that the formula for fk of psi k equal to maximum 0 less than or equal to xk less than or equal to minimum of mk comma psi k by ck into fk of xk product fk minus 1 of psi k minus ck into xk. Here we take the values for k from n minus 1 up to 2. At first stage, we get the formula as f1 into psi1 is equal to maximum of f1 of x1, where psi1 varies from 0, 1, 3, 4, 5, 6 and 7. We can put the values for x1 be 0, 1 and 2. If we put psi1 is equal to 0, we get the value is 0.6. If psi1 equal to 1, we get the value 0.7. If psi1 equal to 3 or more than 3, we get the value 0.7. which is demonstrated in the table below. At second stage, we put k equal to 2 in the first equation. We get this formula. Here we substitute the values for xi to be 7, 4 and 1. If we substitute the value for xi to be 7, the value of f2 of 7 is equal to 0.63. If the value of psi2 equal to 4, we get the value b 0.56. If we substitute psi2 equal to 1, we get 0.56, and the table is given like this. At final stage, if we substitute k equal to 3 in the equation, we get f3 of 7 equal to maximum of f3 of x3 into f2 of 7 minus 3x3. At the value of psi3 equal to 7, we get the value 0.504. From the table, we get the maximum value for x3 equal to 2, x3, x2 and x1. The value of x1 equal to 1, x2 equal to 2 and x3 equal to 2. The maximum reliability is 0.504 at which cost can be calculated using the following equation. Summation j equal to 1 to 3 cj of 1 plus xij. If we solve this, we get the cost be 16. In chapter 4 presents the conclusion of the project. It summarizes the main findings and highlights of the usefulness of dynamic programming in solving reliability problems in space mission system. The chapter emphasizes that the technique is effective for handling complex reliability models and can assist in making better design and decision making strategies. In this project, we have examined and evaluated the use of dynamic programming approaches for dependability modeling in space missions by breaking down the reliability problem into manageable steps and optimizing choices at each one. Dynamic programming offers a methodical and effective way to deal with this difficulty. The entire system reliability can be increased while taking limitations like weight, cost and scarce resources into account by utilizing the optimality principle. The overall project provides a clear understanding of dynamic programming techniques can be applied to reliability model in space mission. The structure of the project, along with the theoretical explanation and numerical examples, makes the study informative and useful for understanding the role of optimization techniques in reliability analysis. Here I have attached some references. Thank you.